Sorry.
Now I did.
Oh, man, I'm sorry about that.
Okay, so just for the folks at home, we started with a path, trail, walk, defined them, then talked about a closed path, trail, and walk, and we're about to prove that every trail, UV trail, when I say UV trail, that means I start at U and I end at V. Every UV trail contains a UV path. And just remind me again what the possible difference between a trail and a path? Do I?
Trails allow you to repeat vertices.
Trail allows me to repeat vertices. Okay, so I want to prove that. Take a minute. One more time, I'm trying to prove that every UV trail contains a UV path. By the way, in this picture, this was a UV trail, right? No edges were repeated. This was a UV trail. Can you find a UV path? Someone give me the finger. Okay, so I'll start here, obviously at U, which I do. Okay, if I keep on going through, stop here, and go here, then I'm good. Okay? Okay, so every UV path, so I want to prove this. Okay, let T be a UV trail. If T doesn't repeat any vertices, if it doesn't repeat any vertices, then what? Oh. Then T is a path, and we're done. And we're done. So, since clearly trails allow us to repeat vertices, so let T is a trail with repeated vertices. Sorry, a UV trail with repeated vertices. Okay, so it starts at U and ends at V. Now, we have the advantage, at this moment, we have the advantage that these are finite graphs. Okay, whole different story if we allow there to be an infinite number of vertices. And there are such things. And we're not going to spend, bless you, we're not going to spend we're not going to spend more than an epsilon amount of time on infinite graphs. Okay, but you should know that they exist. There was nothing that disallows us from having the vertex set be an infinite set, the edge set be infinite. There's nothing that disallows us from the definition. But once you allow an infinite set of vertices and an infinite set of edges, the problems become a little stranger. Okay, so let T be a UV trail with repeated vertices. Again, if you had T was a UV trail with no repeated vertices, it would be a path we'd be done. So let's imagine, let's say W before I say W, let them find the shortest UV subtrail. What would a subtrail be? What do we mean by a subtrail? So I have a trail.
Is it just non-form?
It could be just like a subset. It could be the same set, or it could be a trail that is a sub-piece of the original trail. Okay, is that clear? One more time. Here's a subtrail. Here's a subtrail. So I go down here. I go over here. Let's see, how did I draw this? So I start here. I go. How did I do this originally? Like that? Mm-hmm. Okay, so let's see. I come here. Here's a subtrail. Come down here, over to here, around, up, up, up. So one more time. Here's a subtrail. Sorry. Let's try that again. And, oh, that's the whole trail. No. Okay, so we want to be able to eliminate vertices. So let's see, where can I eliminate vertex? So, and not make a path up. So if I go down the trail, I start at the trail, and I come and I go. So the trail goes like this, and instead of going, so we'll go like this, here. So here's a subtrail. Why do I keep doing this? I should put direction on this. Oh yeah, here we go. Sorry. So here is a subtrail of the original trail. Right? You have to be able to follow the edges that were in the original trail. Okay? So that's a subtrail. Notice I've left out some of the edges in the original trail. Okay, so find a shortest UV subtrail of T. So again, I start with a UV trail with repeated vertices, and I find a shortest subtrail of T, UV subtrail. So I start at U. So here is the shortest one, V2, V3, up to VK, and then the vertex V. This is the shortest one. It contains the fewest number of edges. Okay. But what if this, it's a trail, so it's allowed to have repeated what? Vertices. Okay, and it's the shortest, meaning that it has the fewest vertices. It's the shortest subtrail. So suppose there's a vertex that's repeated. So suppose VI and VJ were the same. Suppose VI is equal to VJ. So I'm going to draw a picture. So I started U. Here's V1. Here's V2. Here's VI. Here's VI plus 1. And some point later, here is VJ. Let's see. Here's VJ minus 1. Here's VJ. And then I continue to go, and I end up at VK. So looking at the picture, can you come up with a shorter trail? A shorter trail. Looking at that picture, can you come up with a shorter, let's see, this is VK, this is VK, which is the, can you come up with a shorter trail? Let's see, what if I started at U, and I went down to VI, and I forgot, let's forget all this stuff. U, V1, V2, VI, and then down to VK. So that would even be shorter than what I have written down here. So if a vertex repeats, I can make a shorter subtrail. Wait a second, what did I just say? If a vertex repeats, then I can find a shorter subtrail. So the shortest subtrail, the shortest subtrail has no repeated vertices. No repeated vertices. Oh, but if it has no repeated vertices, then what? Then it's a path. Therefore, the shortest subtrail is a path. Is that clear? Sometimes pictures help. So that's where you can draw a lot of the details from for the proofs that you're trying to do. Questions about that?
When we're trying to do a proof, can we just draw the picture?
No. Sorry. Let me answer that. A picture helps to put the words together. Okay. So like I drew a picture, the picture helps develop the words. Okay. Proof by picture is not acceptable. Okay. I need the details. Even though I understand, and the picture probably convinces me that you understand, you need to be able to argue this out. Because pictures won't always answer the problems that we're asked in graph theory. Okay? Okay, that's a good question, but... Okay, so what I'm going to go back to page 36. Okay, and let's look at number 5. So just for a moment, I want to point out that number 5, show that in any UV walk, that it contains a UV path. And in fact, that's what we showed. We showed that, in fact, any UV walk contains a UV trail, because if you repeat an edge, then you can eliminate it. And then it must contain a subtrail that is a path, a UV path. So again, 5 is a little bit more general. Show that in any UV walk there is a UV path. The same argument. Instead of starting with every trail, I would say every UV walk contains a UV path. Okay? If it contains no repeated vertex, then you're done. Notice, if it contains a repeated edge, then it contains repeated vertices. So find a repeated vertex, eliminate part of the walk, and now you have a shorter walk. The shortest such walk will give you a path. Okay? Now, those are details. That's sort of the details that we have here. Okay. Questions about that? Okay, so remind me what a circuit is. A circuit is a closed trail. And what's a cycle? Closed path. So now number 6 is asking, show that any circuit in a graph contains a cycle. So what's the difference between a circuit, a a circuit is a what? Closed trail. And a trail that's different than a closed path would include repeated vertices. So I'm gonna draw a picture. So when I have we have a closed. Would you believe I just threw my back out? Sorry, I have a circuit, so I have a closed trail. So there's my closed trail, right? Just because there's my closed trail. One more time. Start at U, go around, and there's my closed trail. Just looking at the picture, can you find a closed path? Can you find a closed path? Okay. Who wants to help me out?
Does it have to start at U?
What do you mean? I mean, it's got to contain U. Sorry. Yes. I mean, it actually contains many, right, closed paths. There's a closed path. Okay, so it contains many cycles. It could contain many cycles. But I want a cycle that contains U and V. Okay, so this was a closed trail, closed UV trail. So the last edge goes from U to V. I want a closed path that contains U and V. Okay, can you write some words down that will prove that?
You're saying in general, right? Not that specific one?
Oh yeah, in general, yes. Well, I've done that one.
Yeah.
So you can talk to your table mates.
Okay, so we're saying that we're trying to show that a closed walk contains a closed.
Yeah. I think. Did you say trail?
A trail.
Circuit 是包含
closed
cycle.
trail contains a closed. Okay.
Think of a closed.
So I want to show that a closed trail contains a closed path.
Closed trail contains a closed path.
Oh yeah, I can remember.
So that's number 6. That any circuit contains a cycle.
像我想看，就是我觉得就是还跟这个一样，先分两类。就是如果它没有的时候，它就本身就是；如果它有的话，其实我觉得更简单。
Except for U and V
找到那个
are connected at the end. Right.
就是它重复的点开始的。
I feel like that's pretty much all I want to say. Add, you know, take that thing, add one more edge to the end, and then one more vertex being.
因为它是个圈儿。
So basically,
So I
anytime
mean, you could repeat the entire argument.
okay, but like anytime it goes off or repeats,
The shortest circuit would be a cycle.
你还是可以
Right. Well, actually, this proof that we did over there was kind of counterexample.
但是它那样就
Or, I'm
最
sorry.
常见的存在，就是你只要是
Those are your questions.
Because we assume that
如果
the
你
smallest
说不
it's
就
the
变
shortest
成
path, then you go and find the shortest path.
它就会变成
Go to the assumption.
Oh, that's
或者我可以，就
trust
是我
me.
们能不
These
能
are
用这
It's
个，
actually
different sorts of.
minimum counterexample argument.
就是除开最后从没到 V 的话，它实际上就是一个 trail。
Had repeated
然后找到
paths
这个
anyway.
trail 的 path，然后再把那个在这个基础上把那个 UV 点上，就是一个 trail， 就是一个 cycle。
可是 circuit 不是
But if you take that as a theorem,
对 circuit
then you could
circuit
find
一点是
yourself
收
a
尾
trail
相
from
连，
U
你
to
就
V,
把它那个
not containing
一
the
段
edges.
去掉，它肯定是有一个，就
Right.
是
So that could be
一
like a
段
two-line proof.
就是你找一个
我懂你的
对，你
意思
懂吧？，它
就是在它
Yeah.
上一个
You don't
点
have to write the whole thing.
对
是吗？然后最后那一段就是肯定的。
对，你随便去掉一个
But I don't think that's what
就可以了。
Right.
然后到时候
And,
再把
and
这
in,
个按
yeah, and in fact, we never said that that trail was not closed. So I feel like that still applies for a closed trail.
For a closed trail, there's a closed trail. Is that what
没有
you?
别的步骤啊。
Well,
我觉得应该有
Well,
的
okay,
我
we
不知道
never
它是不是
specifically said U and V are different points.
是应
So
该
I feel like
yeah,
that,
yeah,
so I feel
yes.
like that it still applies.
Right. Yeah, absolutely.
你喝的那个叫什么名字？
Pink Drink，但是今天他给我做的很失败。
在家吃火锅都我最喜欢在这儿吃，不要睡觉。
我想我看，我看看我。
So let me just sort of tell you a little bit about the difficulty with writing graph theory proofs. There are things that look so obvious. You know, you're just going to clearly this is the case. But what's important is that you practice writing down the details for things like paths and trails and walks, and how you come up with the idea of a cycle from a closed trail or a closed walk. Okay, so I'll assume that you're able to do that. And now I want to look at problems where we're doing a lot about. But that was number 6. Now I want to do something about counting the number of edges. A lot of what we're going to do is going to be counting edges. So how many of you were able to get number 7 again from page 36? G is a graph of order n. The min degree is greater than 1/2 times n minus 1. Greater than or equal to. Show that any two non-adjacent points have a common neighbor. Okay? If you didn't finish that or were not comfortable with your proof of that, take a minute, think about how you would or did prove it. Show means proof. Show, when it says show, that's the soft way of saying prove. Show beyond the shadow of a doubt.
The number of vertices, right? And the number of edges is the size.
Yeah.
Okay, so you might read that as prove that any two non-adjacent vertices in G have a common neighbor.
The vertex with the minimum degree.
Well, it's not the vertex, it's just the degree of it.
Oh, okay.
There might be many.
Yes, okay. Degree.
It's just
And I can't stress enough, a picture helps a lot. So suppose I choose two non-adjacent vertices. Two non-adjacent vertices. Non-adjacent means there's no edge here. No edge. How many more vertices are there in this graph? We're going to assume this graph has n vertices. So G is a graph of order n with min degree greater than or equal to n minus 1 over 2. Okay, so the min degree is greater than or equal to n minus 1 over 2. Show that any two non-adjacent vertices have a common neighbor. So here are two non-adjacent vertices. And this one has a neighborhood, and this one has a neighborhood. So here's how I would prove this. Let x and y be two vertices, two non-adjacent Non-adjacent, that's important. Non-adjacent vertices of G. How many points other than x and y are there in this graph? N minus 2. Okay. Now, if they don't have any common adjacencies, there are. Well, I'm going to make a third hole here, third bunch. These are the neighbors of x. These are the neighbors of y, and these are the neighbors of neither. I'll just call these neither. So what can you tell me about the size of the neighborhood of x plus the size of neither plus the size of the neighbors of y? Bless you.
Excuse me.
Anybody? Okay, just to make it easier, so what is how big is the neighborhood of x? Degree of x. So I've got the degree of x plus the degree of y plus let's call this, and we used n plus n. That's the number of vertices in neither. How many vertices are there here? And what? In the whole thing, just down here at this level, how many vertices are there? N minus 2. So this is equal to n minus 2. Okay, one more time. I need to know. Okay, so what would that tell me about the sum? Let's see. So the sum of the degrees. So what can you tell me about the degree of x plus the degree of y compared to n minus 2? How do they compare? Do what? Which one? Greater than?
Yes.
Why?
Less or equal because the
Yeah, because this may be something. This may have something in it. May have nothing, but certainly I know that this is less than or equal to n minus 2. Is that clear? Is that clear? Oh, but what was the assumption? The assumption was that the min degree is greater than or equal to 1/2 times n minus 1. So the degree of x is greater than or equal to n minus 1 over 2. And the degree of y is greater than or equal to n minus 1 over 2. Is that clear? The smallest degree is greater than or equal to n minus, one more time, that's from the problem. The smallest degree is bounded by n minus 1 over 2. Little delta. We have gone through that, right? Yeah? Okay, so the degree of x is at least n minus 1 over 2. The degree of y is at least n minus 1 over 2. And according to this inequality, this has got to be less than or equal to n minus 2. So what? Is that okay? What is n minus 1 over 2 plus n minus 1 over 2? Okay, so what does this show us? That says that n minus 1 is less than or equal to. Is that okay? No, that's a contradiction. That's how I'll write contradiction. So what did we assume? We assumed that the degree. Let's see. We assumed that there was no common neighbor. Okay. So since n minus 1 is not less than or equal to n minus 2, x and y must have a common neighbor. Okay, if you're going to stop me if you don't understand a particular step. Okay? Again, this is problem number 6 from the book. It's 5. No. You have a question? Okay, wait a minute. Well, so where does it? Okay, so that's from. Where does it come from? It comes from the book. Okay, so one more time. Let G be a graph of order at least 2, such that the min degree is greater than or equal to 1/2 n minus 1 over 2. Okay, that's an assumption. We're assuming this. Assume the min degree is greater than or equal to n minus 1 over 2. Okay? Show that any two non-adjacent vertices have a common neighbor. So we're going to prove this by contradiction. We're going to assume it by contradiction by assuming that they don't have a common neighbor. They don't have a common neighbor. If they don't have a common neighbor, then we have the neighborhood of x, the neighborhood of y, and maybe some more. Okay, so and notice the degree of x is equal to the size of n of x. And the degree of y is equal to the size, the number of vertices in n of y. So the degree of x plus the degree of y is less than or equal to, let's see, this could be empty. Here are 2 points. The total number of vertices in this whole graph is n, so this must be less than or equal to n minus 2. Is that clear? Since there are 2 vertices here, then the sum of these 2 sets must be less than or equal to n minus 2. Does that answer? Okay.
Go to the next line.
Okay. So let this line?
This one, the n minus 1 over 2. So I'm okay on degree x plus degree y.
So where am I? This one?
Yes.
Okay.
How'd you get from the one before that to that?
From here to here?
Yeah.
Hold on. Oh, yeah. So, because the min degree is at least n minus 1 over 2. Okay, so the degree of x is at least n minus 1 over 2. The degree of y is at least n minus 1 over 2. And it's less than or equal. So one more time, let's put these in. So this is greater than or equal to, and this is greater than or equal to. Okay, so this is still less than, this is bigger than this, but this is still less than n minus 2, but that's a contradiction. Okay, sorry. If I'm jumping, it's obvious to me sometimes. And sometimes it's not so obvious to you. So you need to stop me and ask exactly that question. So one more time, the degree of x plus the degree of y plus these other vertices is equal to n minus 2. Is that clear? Okay, because here are 2 vertices, and here's everything else. There are vertices adjacent to x, there's vertices adjacent to y, and there's possibly vertices that are adjacent to neither. So the degree of x plus the degree of y plus the number of vertices that are adjacent to neither is equal to n minus 2. Then we get a bound of the degree of x plus the degree of y, and we get a contradiction. Questions? Okay. All right, so I want you now to look at problem number 8. Okay, let G be an NM graph such that the number of edges is greater than n minus 1 over 2. Sorry, n minus 1 choose 2. Show that G is connected.
Is big N there n of x plus n of y?
This big, no, it's just the size of these neither points. So here are 2 points. The whole graph has n vertices in it. Here are 2 points. So what's down here is n minus 2. What's down here is n minus 2. So there's points adjacent to x, there's points adjacent to y, and there's points adjacent to neither. Okay? Okay, so one more time. Number 7. Let's see, number 8. Let G be an NM graph. What's an NM graph? NM. And what?
N vertices and M edges.
M edges, good. N vertices, M edges, such that M is greater than n minus 1 choose 2. show that G is connected.
I guess if there exists a path, then there exists a walk. Though.
Yeah.
Okay.
If there's a walk, there's a path.
Did I say that backwards? Yeah. And the other way around, right? Okay.
Actually, yeah.
Yeah. Okay. Okay. So connected means there exists a path in between any two graphs. Graph, right? Okay.
I'm not sure this is.
So it's like my assumption of how this is going to work.
We'll talk about it.
If you assume it's disconnected with restraints on the number of edges, you end up with an edge that's kind of like floating in vertices that's connected to you.
Edge without vertices.
So let me just, you all know this notation, right? N minus 1 choose 2?
So it would have to be connected.
Why is there an edge with
N minus 1 choose 2? Or K choose 2?
What I think is...
I think we talked about this on the first day.
Yes.
K choose 2 is equal to...
You assume it's disconnected.
K choose 2, there's a formula for this. K factorial. Is that right?
Yeah. We can simplify it, but I think it's right.
Okay. By the way, this is, let me just point out that that's K times K minus 1 over 2. What? How did that happen? Let's just make sure we're all on the same page. K factorial is K times K minus 1 times K minus 2 times K minus 3 times K minus 2 factorial. That's K factorial over 2 factorial, which is just 2, and K minus 2 factorial. So it might be a little bit easier to get rid of the factorials if we just note that K choose 2 is equal to K times K minus 1 choose 2. Divided by 2. Okay?
So
You're all looking at me, you're all looking at that board going, huh? Let's try this again. Everybody does see that K choose 2 is K factorial over 2 factorial times K minus 2 factorial, which is equal to, K factorial is K times K minus 1, let me write this out, times K minus 2 factorial. Okay, that's K factorial, K times K minus 1 times K minus 2, K minus 3, K minus 4, and so forth. But we'll abbreviate all the rest here by K minus 2 factorial. And then 2 over K minus 2 factorial, and then these cancel. So we get K times K minus 1 over 2. Yes? Okay?
do you remember?
Okay, if we have the connected graph, how many edges? Or I'm sorry, the complete graph, how many edges it has compared to the vertices?
It's a great question. Very appropriate for me.
Yeah.
So there's two ways to think about it. There's how many pairs of vertices are there.
Okay.
Which would be n choose 2.
Right.
From a group of n things, how many ways are there? Choose 2.
Okay. Yeah.
You can also work with like degree sum stuff, right? A vertex has degree n minus 1. And there's n. So that's n times n minus 1 equals the number of edges times 2.
Okay. Gotcha.
So divide by 2.
Okay. Okay. And then let me think. So if we had two separate complete graphs, given some number of vertices, I think the maximum number of edges would be if we, I don't know, I'm trying to figure out if that was like if all the vertices are in one and then you have one lonely one over here, or if we have an even spread.
Right.
And so I want to say the even spread gives the maximum number of edges. But okay, because whatever the case may be, basically say we have figure out what distribution is going to give us the maximum number of edges, and then I think that number will be less than this. Now I gotta get to work.
So n minus 1 choose 2.
他假设 x y 之间它没有
that's
Oh, yeah, that's just n minus 1.
So that's a complete graph of n minus 1 vertices, right?
Right. Mm-hmm.
So it might give you a hint that, if you have one loner vertex and n minus 1 complete graph of it, that's the most you can do. So that might give you a hint on the direction to go.
Anybody want to start me off here?
Okay, there, and it's got to be greater than that. Good. I think we got it.
Well, you have to prove that that's the biggest one, right? You have to show
right. Okay. Okay. So we're basically adding n minus 1, choose 2.
Anybody have an idea they want to try? I'll help push it through.
So suppose you have a graph.
对，是给大了，是给了很大的价。就是因为给大，所以你才能证它确实不可能是不可能。
Suppose you had k over here and n minus k over here.
它肯定给的范围很大，就是如果你其实一个 m_n 的 graph 要做 connected， 其实你只要 m 等于 n 就可以。但是你如果 m 大到这种程度的话，它就一定不可能。就是我知道为什么，但是我不知道怎么说。
可是如果你能证明，对，那也不是。
就是你其实说挺好说，就是因为
其他的都相当于其他都是 complex， 不是 complete。就是这个
对，
就可能
就是 n 减一个 complete 再加一个点连上去。
对啊。
So there might be some combination of some common denominator.
就这么一个图形，就是一个。
对，我们要证每一个都是。我们要证它必是，所以我们不能说只挑出来一个说这个是。我们要证它必是，所以我们就一定要说不可能不是。
J components.
Anybody got an idea they want to try? Otherwise, I'll give you a hint.
So just kind of going off, we've been doing contradictions, so keeping up with that, we can assume that G is disconnected.
Okay, assume that G is disconnected.
Right.
Okay? So, and this is how I draw disconnected pieces, and there may be more than two.
Right.
Okay?
So we have two or more connected graphs.
Right.
And now let's say those are all complete graphs.
Great.
Then we have...
So let's say there's A points here.
Yeah.
And B points here. Okay?
Okay, so then we have... okay, and then so it's it's A minus 1 choose 2.
Whoa, sorry. So you could. This doesn't have to not be complete. That's a lot of knots. This could be complete.
Could be complete, right?
On A vertices.
Yep.
How many edges in a complete graph on A vertices?
So A choose 2 if it's complete.
Okay. So I know that there's at most A choose 2 edges here. And I know what's the maximum number of edges here? B choose 2. And I know that A plus B is less than or equal to n. Okay, can you work out the algebra? N minus 1 choose 2 is a lot of edges. So this actually goes back to a calculus problem. Your favorite. How do you maximize and minimize the sum of I want to maximize the sum of two numbers. So if we know that A plus B is less than or equal to n, the maximum is going to occur, and you can graph this at a critical point, either when they're equal, n over 2, n over 2, or when they hit the boundary points. Can't hit the boundary points, and then you have to work your way down. So you got to use a little calculus to do this problem. Okay, right? We can write, if we assume that A plus B is equal to n, which we might as well assume that there's no third piece. If we assume that A plus B is equal to n, then we can maximize that sum. Can't be n. A can't be n and B be 0. A can't be n minus 1 and B be 1. And the maximum occurs maybe when A is n minus 2 and B is 2, but then that's not enough edges. Okay, so one of the things that we're going to have to rely on is, and we'll go through some of the details at some later point when it becomes a little bit more reasonable. We're going to have to look at max and min values and probably be taking write things in terms of a variable, in this case n being the number of points, and then maximize it or minimize it. But let me give you a little different way to go about this problem. Okay, what if, let's look at the max degree. What's the largest degree that this graph can have? Okay, so one more time. So let's assume that the max degree, if the max degree is n minus 1, the max degree is n minus 1, the graph has n vertices. If the max degree is n minus 1, then what? Okay, the whole graph has n vertices. The max degree is n minus 1. Don't lose sight of what you're trying to prove. That's n minus 1. That's all the vertices. Is this graph connected? Remember, that's what you're trying to prove. You're trying to prove that this graph is connected. So if the max degree is equal to n minus 1, we're done. Is that clear? What do we mean we're done? What do we mean? We have to show that every pair of vertices have a common neighbor. What do we have to show? No, we have to show that that the number of edges show that G is connected. Sorry, you have to show it's connected. Is that graph connected? Choose any two vertices. If you choose the center vertex, then the other vertex is one of the things that hang off. If you choose two of the vertices down here, if you choose two of the vertices here, to be connected means that there's a path from this vertex to this vertex, and that's easy to find. Okay. Okay. So if it doesn't have degree n, if it doesn't have degree n minus 1, what if it has max degree n minus 2? Okay, what does that graph look like? So it has max degree n minus 2. And remember, I'm trying to show that this graph is connected. So we can do that directly. This is my vertex of degree. This is my vertex x. Here are n minus 2 other vertices. How many more vertices in this graph? One more. So if there are no more, if this vertex is adjacent to nothing here, if this vertex is adjacent to nothing here, then how many vertices, how many edges can I have? One more time. If this is adjacent to nothing over here, how many edges could I have? How many vertices are over here? N minus 1. So I can have at most n minus 1 choose 2 edges over here. But what does the problem say? What does the problem say? I have.
Show that the edges have to be greater.
Wait, so it says now don't lose sight. It says such that m is the number of edges, is strictly greater than n minus 1 choose 2. So the graph can't look like this. Right? The graph can't look like this. This is one piece and that's all by itself. Because if it looked like that, then the number of edges that I would have would be n minus 1 choose 2. But it says we have m, which is the number of edges, is greater than, strictly greater than n minus 1 choose 2. So if it's strictly greater than, then this must have an edge somewhere over here. And if that has an edge to one of the points down here, then this vertex, what do we call it, x? This vertex x has a path to, I can't call it x, this is x. Let's call it y. This vertex y has a path to any other vertex. It has a path to x, so it takes y to here, and it takes y to here, to any of the other vertices in the neighborhood of this point. And it's connected. Okay, and that's all you have to prove, is that this graph is connected. Okay, so if the min degree is if the max degree is n minus 1, we're done. If the max degree is n minus 2, we're done. Then the max degree is less than or equal to n minus 3. Okay, so what does that look like? So what do I have? I have that the number of edges is greater than n minus 1 choose 2. So let's do a count. The max degree is what? What did I say? Max degree is less than or equal to n minus 2 vertices here. N minus 3 vertices here. Okay, that's the max degree. How many more vertices do I have? 2 more. Now it's a matter of showing that either I don't have enough edges, and what's the number of edges that I was given, that the number of edges is greater than n minus 1 choose 2. That's a lot of edges. So here's the thing. Suppose each of these vertices send an edge to one of those n minus 3 vertices. Suppose this sends an edge here and this sends an edge. Notice, it can't send an edge here. If this vertex is adjacent to this, then that would contradict that the max degree is less than or equal to n minus 3. Okay, so if this sends an edge here, and this sends an edge here, then the graph, what's the maximum number of edges that this graph can have? Well, in fact, you don't need that. It's connected. You're trying to show that the graph is connected. So what does that mean? That at least one of these vertices sends nothing to all those points. Okay, and now it's a matter of just counting the number of edges. Okay, so this is connected. By the way, if they both send no vertices, if they both send no edges over there, you don't have enough edges. Remember, we got a lot of edges. We got the number of edges is strictly greater than n minus 1 choose 2. That's a lot of edges. Let me start. If I look at this vertex and these three, that's only n minus 2 choose 2. It's only n minus 2 choose 2. We have to get up to greater than n minus 1 choose 2. So if both of these vertices send an edge here, then the whole graph is connected. How do I know they're connected? Well, this can get to this point here, and then it can get through this point, it can get to everything else. And the same goes for this one. And remember, that's what you're trying to show. That if the number of edges is strictly greater than n minus 1 choose 2, then the graph G is connected. Okay, so it's several different cases. So what I'd like you to do for Thursday, this is not to be turned in yet, and I'm working on a first homework to be turned in. For Thursday, you should write down all the details of problem number 8 on page 36. In your book, and then we'll go through it again. Okay? Okay, questions? Okay, now, leading from problem number 8. If it has more than n minus 1 choose 2 edges, it's connected. If it has more than n minus 1 choose 2 edges, it's connected. Construct a disconnected graph of order n and size. What does size mean? Number of edges. Okay, so for n greater than or equal, construct a disconnected graph of order n and size n minus 1 choose 2. This is like a trick question. Number 9, can you do that?
Well, since you just said it's a trick question.
Well, that's not true. It's like, of course. Disconnected graph with n minus 1 choose 2 edges. Notice, one more time, if it has more than n minus 1 choose 2 edges, strictly more than n minus 1 choose 2, it's connected. I want a disconnected graph with n minus 1 choose 2 edges, and it's disconnected. And you're thinking too long. So this n minus 1 choose 2. Every time you see something k choose 2, n minus 1 choose 2, m choose 2, the first thing, bells should be going off whenever I say something choose 2, because I'm thinking a complete graph. Okay? I'm thinking a complete graph. So I need a disconnected graph with n minus 1 choose 2 edges. Disconnected. Okay, does that graph have order n? Does everybody see the graph? Right, there's the graph. Kn minus 1 union k1. Kn minus 1 union k1. The total number of edges in this graph, total number of edges. And someone's saying, n minus 1 choose 2, total number of edges here. And notice the problem before said, if I have more than n minus 1 choose 2, it's connected. So this is the breaking point. Here is a graph that has exactly n minus 1 choose 2, and it's disconnected. Okay? Okay, I can't stress enough. Be working on these problems, be drawing lots of graphs. Okay, let's see. Remind me, what's the relationship between the edges and the degrees? What's the relationship? I always forget this. That was theorem 1. The sum of the degrees is what? Twice the number of edges. Okay, let's see. So let G be a disconnected graph of order 5. I'm on problem number 10. What is the largest possible, a disconnected graph of order 5? What is the, 5 is pretty small, so. What is the largest possible value for E of G? G is the number of edges. If G is a disconnected graph of order n greater than or equal to, what is the largest possible value for E of G? So change 5 to any number you want. Where is the maximum number of edges going to occur? Five is pretty small. You should. Anybody? One more time. Let's read the problem. G is a disconnected graph of order 5. What is the largest possible value for the number of edges? 6. How'd you get 6? Do what? Okay, so 4 choose 2 plus 0. And the graph attained on 5 vertices is K4 union K1. Okay. Okay, construct a, so let's see, what was that? What is the largest possible value of G? If G is a disconnected graph for any n, what is the largest possible number of edges? So the number of edges, so the graph would look like kn minus 1 union k1. Okay, and the number of edges here, of course, is n minus 1 choose 2. And there are no edges from this vertex to this set. This is the largest possible for a disconnected graph of order n. So where would the smallest, if I have a graph with 2 components, what's the smallest number of edges on a graph on n vertices? Smallest number of edges on a graph on n vertices. Yeah, that's not going to work. Because here's the smallest number of edges on the n vertices. 0. But if I have 2 components, this goes back to calculus now. If we have a graph with exactly 2 components, that's not going to work either. If I have a graph with exactly 2 complete components, I'll get there. 2 complete components. What's the smallest number of edges? Okay, and this goes back to the max-min problems you did in calculus 1. So the minimum is going to occur kn minus 1 over 2, kn plus 1 over 2, and kn minus 1 over 2, and we've got to take the floor function and ceiling function. Okay, if n is odd, it's n plus 1 over 2 and n minus 1 over 2, and if n is even, it's n over 2 and n over 2. That would be the smallest number of points, of edges. Okay, and these are calculus problems hidden amongst this graph theory. So we're going to need to pull from a lot of the mathematics that we've done previously. Okay? Not much about limits, but certainly whatever you did about counting. Okay, so I'll tell you that there will be a substitute on Thursday, but he has instructions to cover the rest of Chapter 5, which includes, the rest of Chapter 1, which includes Section 1.5, and then he's going to go over some problems with you. And before the weekend, or maybe over the weekend, I'll come up with assignment number 1. Okay, and that will be to turn in, to hand in. Okay? Questions? I won't see you Thursday. I'll see you next Tuesday. Michael Phillips.
Oh, okay. I thought he was...
He's leaving. But school in Beijing doesn't start till February 15th.
Oh, Michael.
Yeah.
很累，是不是要去上那个手语？
他课还早，问卷课间他就发了。
Just take that red, see that thing?